Is it working?
It does.
Okay.
How do I point?
Okay, so now we have Claudio that will tell us about switches, new physics, also with the entangled tops.
Yeah, so as I was saying before, this is the natural follow-up of Luca, who was also the follow-up of the one previous. So this is on the same topic. But before I get into the business, okay. I wanted to say something about this because this is very cool, I think, and I think there are some points to be made about these results. So of course we have this, which is very embarrassing for the Monte Carlo community as a whole, because I mean this should never happen. Okay, hopefully this will be understood in a fairly short period of time. But we also have this. So if you assume that nature lies, the standard model lies somewhere in here, and then you have nature over here, I mean, you have quite a sizable shift. And then you have, I'm offsetting every time I move forward. Okay, I can stay here. And then you have, if you want, a slight overshoot over here, and then you end up with something consistent with predictions at 500 or more. So this is what we were saying before. There's no way to accommodate a deviation that shrinks with energy, for example, with an EFT. So this is calling for some kind of resonance or some kind of localized effect around threshold that then kind of dies off. Now, I mean, fine, this is, our confidence level is very high in saying this is probably mismodeling, but it still makes sense to ask, you know, what if? And we have seen this plot before, but it is very well known that near TT bar threshold there may be, there are pseudo-bound state effects. Of course, it depends on color. You're only bound if you're in a specific color configuration. But nevertheless, you still have bound states. And so you can ask, regardless of the calculations that have been made that are very hard to do and to reproduce, but you can ask, okay, can I accommodate something, you know, some very general kind of localized resonance, which can give me a deviation similar to the one that Atlas is seeing? You know, maybe you can't, and then it's, you know, and then you stop thinking about it. So what you end up doing if this kind of new structure can simply be added, or if the interference and the square behave similarly, is that what you end up observing is, of course, the weighted average between the standard model and the amount of signal that you inject. And the amount of signal that you inject to be the most favorable possible, since Atlas is seeing a lower fluctuation or deviation of D, the lowest D can be is -1 if you have a pseudoscalar, a perfect pseudoscalar. And so how about we inject some amount of pseudoscalar with D equal -1 to accommodate this? And I mean, amazing. Thank you. Okay. Okay. And so simply by counting, you know, one takes Pythia to be my standard model prediction, and then how much do you need to go down to go down to have this kind of spread. And it turns out that you need 15% contribution from something with D equals -1. Of course, you can think, okay, if my new signal doesn't have D equals -1, but has D equals -0.6, then you need, you know, a lot more. But in the most favorable case, you need to inject about 15%. And then, since this guy has 3 parameters, coupling, mass, and width, and you have given us 3 measurements, we can accommodate it perfectly. So this is some super quick simulation. The solid line is the standard model. The dashed is what happens if you inject this amount of pseudoscalar. And you see that at threshold, you go down, and the integral between 340 and 380 is exactly what you get. And then, since we are sophisticated, here you are slightly above, and here you are slightly above. It's 3 parameters and 3 measurements. I mean, what do you expect? It's long gone. Okay, so threshold. Okay. So to be slightly more serious, the moment you add this amount of signal, essentially for free you get this kind of deviation in the differential cross-section. Like there's no way. You can have more than this, but this I think is the minimum you can have because I'm injecting something that is maximally negative in D. And so I was going to say that there's no way to accommodate a 30% shift at threshold, but then it was brought to my attention that actually measurements of MTT bar at threshold have a very large uncertainty, and so it could be the case, I realized an hour ago, but it could be the case that this is actually not completely crazy to add. But this is a well-defined prediction that, in principle should be testable, and so if it's possible to get the differential cross-section, the unfolded cross-section in these beams, then one would expect a positive contribution from whatever kind of physics you add, toponium, a crazy Higgs. There should be a positive amount of cross-section being injected by this effect. So I don't know how feasible this is, but this would be a very interesting check. This being said, so we have seen something close to this table before. This is a kind of summary of all spin observables that one can conceivably think about. D is our friend, is what is used to determine the presence of entanglement, and it's sensitive to the trace. But there are all sorts of things, and apart from the individual coefficients that enter in the spin density matrix, something that is also interesting to think about is to look at observables defined in a laboratory frame. Because if you remember from previous talks, all of these quantities are defined using angles in the reference frame of the particle that is decaying. And the boost comes with a very, very large uncertainty. So if you could use observables that are defined in the lab frame, now you're not going to be sensitive to spin, purely to spin, of course. You're sensitive to a mixture of spin and kinematics. But reconstructing leptons in the lab frame is the most precise thing that can ever happen inside a detector. And so even though these are not purely sensitive to spin, and so from the point of view of quantum information, they are worse, from the point of view of seeing new physics or characterizing TT bar in a novel way, these may actually be more interesting or more powerful than the individual coefficients. And in fact, there has been a projection done by CMS in which they took all of this and fed it to a neural network, and then asked the neural network what are the most, with a detector simulation, of course, and then asked what are the most important variables. The neural network finds that indeed delta eta, cos phi, and delta phi are those that allow you to find this particular model was SUSY more effectively than the other. So the highest ranked are actually those defined in the lab frame. Even though you have slightly less cleanliness or sensitivity to spin, the resolution is so much better that actually these make a lot of sense. So this is something, again, to keep in mind. Okay, so now I will be looking at two examples of new physics that you can look for, one resonant and one not. And my first example is supersymmetry. Yes, for real. It's not your normal supersymmetry. This is slightly fine-tuned in the sense that you take stop per production, but then you tune the parameters in a way that the mass of the stop and the mass of the neutralino conspire to give you something close to the mass of the top. And so in this diagram, the stops are on shell. This is notoriously hard to find. And so if you look, for example, at the summary plot by CMS for run 1, you see that, or maybe you don't, but I can tell you, the line m stop minus m neutralino equal m top, there is absolutely no constraining power whatsoever. And then you have a similar problem when the difference is mw. But every time you have these degeneracies, by looking at kinematics, you essentially cannot tell apart this signal from regular standard model top production. I mean, okay, you have missing energy, but you don't know it to begin with. So. And so you have this sort of problem. Same with Atlas, and you see very clearly these dips in sensitivity. Again, when the difference in mass is the mass of the top, when the difference in mass is the mass of the B plus the mass of the W, you have another dip, and when they are exactly degenerate, at which point you can't say anything really. However, if you look at spin correlations, this is something that again is known, but just to point out, since you have a fermion structure that is completely different, in this case, because of the different statistics of the particles, you have correlations being strongly, well, strongly, depends on the amount, depends on X, but you have spin correlations decrease, and on the other hand, you have individual polarizations of tops increase. And so again, this is CMS, a projection for Airumi, where they fed all the information that was in the previous slide to try to see if they could explore this region that is not explored by other observables. And it turns out that when you add spin correlations, you go and explore precisely that region. So by adding these new observables that are inspired from quantum mechanics, you can actually explore regions of parameter space that you couldn't explore before. And so here they're able to exclude at 2 sigma this model of stop production up to a mass of the stop of around 600. That if you compare with this, I mean, like it's gigantic, no? It's on the way to here with spin correlations. This is unfair because this is run 1, but I mean, still you have a very significant enhancement. Okay, and my second example is some kind of heavy new physics for which an effective description may be appropriate. Look, I already said everything there is to say. So I'm just going to point out that you have essentially 2 classes of EFT operators that can enter TT bar. You have all sorts of 4 fermion operators, where you have a 4 fermion vertex between the light quarks coming from the proton and tops. Or it kind of depends on the flavor assumption, but in principle you only have one, let's say one class of operators that enter gluon to TT bar, and they automatically give you these 3 interactions, and this will be the top chromomagnetic dipole. So here you have 7. This depends on the flavor assumption that you pick. Our flavor assumption is that this kind of physics is top-philic, so it couples predominantly to tops, or it picks out the 3rd generation, sort of like the Higgs. And these are all color octets in the sense that the TT bar pair that is produced from this interaction is in a color octet state, so it's mimicking this process, but you can also arrange the TAs in a way by essentially removing them. That makes the structural color singlet, which then, of course, wouldn't interfere with the standard model. It would only enter squared. So do I have 5 minutes? Yeah, I have more. OK, very quick aside. You may wonder, if we start introducing these higher dimensional operators, since the process that we see is not TT bar with the tops entering a magnet and then seeing which way they bend, but what we see is a 2 to 6 process, and then by looking at angles from leptons to a specific sum of momenta, we infer that we're measuring spin. You may wonder, if I start adding these higher dimensional operators, they can also go here, they can also go here. Are we still measuring spin? And it turns out that there is a miracle happening, because point number 1, yes, the transfer of the spin state to the decay product still happens. This is general. And furthermore, if you look at the dilepton final state, the spin analyzing power of leptons starts at 1 over lambda to the 4. The first new physics contribution is 1 over lambda to the 4, with this expression that we worked out in front. But if you actually consider the bounds that we already have on these coefficients, and then you evaluate everything, you find that it's an extremely small contribution. So by looking at the dilepton final state, where you have alpha L twice, you're essentially safe in terms of when you measure angles between leptons, you're actually measuring the spin of tops, which is not obvious when you start introducing new physics. But for dileptons, this happens. Leptons plus jet, this is not the case, let me just say. So, OK, now some plots to sell it. This is for the top chromodipole, CTG. And here we plot the difference from the standard model for the observables that we found were most interesting. There was a question before, can we optimize? Not really, but we can tell you which ones are interesting for any operator. And this is a range where it's, let's say, realistic the CTG may lie still. And you see that these different spin correlation coefficients and these observables delta that are inspired from entanglement all deviate in various directions. And so if instead of just measuring D, we could have available a full measurement of the spin density matrix, we could start correlating deviations, and the sensitivity would be greatly enhanced. This is for Fermi operator. Of course, the bound is worse because for Fermi operators only entering QQ bar, and QQ bar is 10%. So it's by design, this is going to be worse constrained. But still, you can see that different observables, well, for instance, now you can see that this operator also changes the individual polarizations of tops, while CTG couldn't. But different observables, again, deviate in different directions. And so you can actually, again, start correlating. You know, I see delta minus be positive, I see BK be negative, okay, then I can say I have a positive value preferred. And this, of course, with just one measurement you cannot do. You have to correlate across different measurements. And finally, as usual, if we can also get differential information, this greatly enhances sensitivity. So here we consider a four-Fermi operator in a Conroe octet so that there is interference with the standard model. And here again we plot the difference from the standard model for a selection of spin polarization and correlation observables. And here we start, there will be a mild cut on cos theta to require these stops to be slightly central, and then we scan in MTT bar. So this is MTT bar less than 420, and you see that in a range that is still allowed by other measurements for this Wilson coefficient, you have percent deviations, meaning nothing, because there's no way to measure these quantities at the percent level. But if you go slightly higher, you start to see a larger effect. And if you go even higher, it blows up. So, and you also start seeing, you know, higher order quadratic effects and not just linear. So even with a relatively mild cut, MTT bar greater than 600, which is not that crazy, you know, to do Bell inequalities you need 1.5 TV. You have an enhancement in sensitivity of a factor of 10. So this is, again, very much dependent on what kind of experimental resolution and what kind of binning you can achieve on these measurements. But in terms of discovery power, it would be, well, first, the more things you can manage to measure, the better. But also, differential distributions are extremely useful. And as usual, going to high PT and high transverse momentum enhances these EFT effects. Okay. So, just a final remark, some kind of idea for how much you can constrain. Already in 2019, when CMS measured the density matrix, the full density matrix, they managed to do a fit for CTG, which was world leading at the time, and it largely still is, showing how spin correlation measurements really are powerful in constraining these operators. We did it again together with Eleni 2 years ago. And we simulated around 3 differential measurements over 9 bins in phase space. Interestingly enough, doing this next to leading order, we actually find a symmetric range, but okay, it doesn't matter. It's still approximately the same. But what we were able to find is that for most of these, for Fermi operators, a 300 femtobarn differential measurement is largely competitive or leading with respect to the global fit we currently have. So this again shows what I was pointing out here, that a differential measurement of these numbers has a gigantic discovery power for new physics, and the correlation across different measurements can also, again, enhance the sensitivity that is achievable. And it could actually be constraining these operators from just one measurement well into the multi-TV scale, which is with a cut in PT, with a maximum cut of 600, you go well into 0 point over TV. So you have this enhancement given by the the number of operators and the differential distribution. Okay, this is all I have. Thank you.
Thanks a lot, Claudio.
I'm not touching anything.
Yes.
Thanks, Claudio. Very interesting. So, if you go back to the first part, when you were showing, where you were discussing the contribution of a possible light resonance pseudoscalar, in particular, on the differential cross section. At some point, this I didn't understand exactly. So you said that this will have a positive effect in terms of. But
it has to be positive.
These pseudoscalars, have interference with the standard model TT bar production, and this interference could be a destructive interference. So what if let's say, if you would have kind of a peak, which is. Is it working? Not working. Okay, still working again. And then you have what we saw many times in this kind of things, kind of a dip at some point close to the threshold. I mean, in this way, you could even accommodate a reduction of the cross section,
so this
or
is,
not.
I mean, you start to become model dependent, but the point is, to start to see the dip, you need a small enough coupling that the square is not dominant, that the interference is dominant, and then you need to kind of tune the mass so that the dip lies, you know, in your first bin. So it's much harder to accommodate. Okay. You can in principle, but it's much harder. If you just, you know, try a random set of couplings, you find a bump, not a dip. You need to tune it to have a dip, even more than it already is.
Okay, clear. May I ask another question? A more general question on this. I mean, whenever we saw, maybe this is just a personal and superficial comment, but whenever we see these limits on many EFT parameters, I don't know, I have in mind this top sector, and in particular, I don't know, this spin coloration thing. When we see the results, we always see the results in terms of limits. But then when we look at the individual results shown by the collaboration, we sometimes see, okay, this we don't understand, here we have a discrepancy. I mean, do we have a way to visualize when we have small discrepancies, small quotation marks excess, even in this EFT picture? Or maybe this is a more general question for everybody. Because, I mean, you said at some point this has discovery potentials, but I see that many times this is kind of presented like we give limits, exclusion limits on the EFT coefficients. And we not really say, okay, here we have 1 sigma, 2 sigma discrepancy there.
So I'll say something, but for sure other people want to comment. Yeah, okay. No, go ahead. So, like you're saying, 1 sigma, 2 sigma in a specific place, in a specific measurement. But the point of DFT is that you correlate across. So, like, you know, you could imagine half a sigma, half a sigma, half a sigma, but they paint a consistent picture. And then when you actually fit your coefficient, you're 2 sigma away, you know. Or you could have a pattern of deviation that does not paint a consistent picture, and then you say, okay, even if I fit, you know, my goodness of fit is bad, but my best fit point is still 0. Or you could have a case where, by correlating many things, you say, no, actually, I'm seeing patterns.
It's sort of a follow-up. So, I mean, you showed CTG, for example, but we constrain this super heavily just from the cross-section, right? My question is more, actually, perfectly on this table. Are there any, I guess there's probably not going to be too many operators that are only going to be constrained really well by these kind of spin entanglement observables, but are there any kind of correlations between particular operators where we can help to break some blind direction or something? I mean, I'm most trying to think of, is there a really good reason that we can't live without some of these operators being measured in these observables compared to other ones where they also have sensitivity?
No, so it depends what you can actually achieve. So if you can achieve something that is similar to what we are projecting here, then you're better than cross-section plus PT plus everything we already have. Or at least you're comparable. With one spin correlation measurement, you become comparable, operator by operator. Because look, minus 0.4, 0.3, and the global fit now is minus 0.4, 0.3. So for QQ18, you're the same. Okay, I mean, But no, but what I'm saying is that, no, but you see it from here, no? Because when CMS did it, this was early run 2, this was 36.1 femtobarn, and they extracted CTG, and it was easily world leading from spin. Easily. And it still is essentially world leading. Just from spin. Complain to them. This one. No, this is the measurement. This is what they got. Yes. Yes.
Just a follow-up of this. So if I correctly understand your question, you ask the difference between the exclusion limits and the discovery limits. In the sense, no, which is the significance with which you can reject zero at the end, no? This is what you're asking.
It's the same.
Yeah, the exclusion limits. You're excluding
No, wait.
When you only see limits published from experiment, then it's hard to judge, that I think was the comment, whether there's a discrepancy that may point at a potential signal that is hidden in the published limit.
Yeah, but when you make a feasibility study, typically what you do is, which is your capability to exclude zero. Okay, then you exclude zero at 5, 4, sigma, level, and so on.
No.
It's a different way to look at the same numbers.
So for projections, of course, we fit. I mean, the best fit point is 0. Like we use the standard model, no, for as a reference. This is coming from the measurement. This is our fit of the measured numbers. These, of course, assume that you're measuring standard model, and then you have a range around 0.
Can you go back to where you showed the expected limits? Yeah, this one or the previous one? So there is a band here, which do you apply some uncertainties or?
This is scale variation, the band, and the inner band is our Monte Carlo.
Like statistics?
Statistics. So the inner band can be improved as you want. The outer band is scale variation.
Okay.
But we stopped running when scale variation was becoming dominant.
And this is NLO?
Approximate NLO.
Yeah, okay. Yes, file.
Yeah, thanks for the nice talk. So in the, like which width did you put for this kind of rest?
So it's fixed by this. So the width is such, the width and the couplings are such that if you take D from 340 to 380, you get precisely this number. Mm-hmm. And the D from 380 to 500, you get precisely that. That gives you the width, because you move away.
So you fit this, because I mean you could take the width of the Bright-Wigner from the toponion, the paper that James was showing, and just include there as a modeling of the toponion, just the mass and the width. And this will be like the Bright-Wigner from the toponion.
I understand that there are going to be some much better Monte Carlo simulations with toponium coming out fairly